I'm here with Dom Salisbury, and he's going to speak about turbulent exchange over Arctic sea ice. And Dom, could you just give us a bit of an overview on the research that you performed?
Sure. So we're interested in turbulent exchange of the Arctic sea ice. This is our project. This was summer 2013 project. The Arctic Cloud Summer Experiment. So really the main aims is to look at low-level stratus cloud in the Arctic. It's really poorly represented in models and kind of poorly parameterized as well. So our project investigates both cloud properties and the boundary layer, turbulent dynamics, and also the thermodynamic structure. This is our cruise track. So we set sail from Norway. We sailed around the Russian side of the Arctic Ocean to Barrow, Alaska. This was a six-week cruise, and then we had a change of crew, and then we had another 6 weeks coming back on this track. And these are just our surface temperature measurements. So these were from an infrared, kind of an infrared laser that we had on the icebreaker. So this post is basically about the turbulent flux measurements, which were taken from the mast at the front of Odin. We had a kind of standard eddy covariance setup, so this is just direct measurements of momentum fluxes, sensible heat fluxes, latent heat fluxes. This is just a time series of our results. Okay, so this is the full 12 weeks. These are our U-turn wind speed measurements. So we have wind speeds from a few meters per second to maximum wind speeds in the second leg of around 14 meters per second. So this is the U star, or kind of a proxy for momentum exchange, sensible heat fluxes, latent heat fluxes. And one of the main things we want to do is relate these fluxes to sea ice concentration, which is kind of the most basic measurement of sea ice that you can get. So what I've done is match up these flux measurements from the ship with satellite-derived ice concentration from different instruments. And there's more on this over here. So what we want to parameterize, our end goal is to parameterize the transfer coefficients for these fluxes. So just focusing on the momentum flux, this is the transfer coefficient for momentum flux, which is commonly known as the drag coefficient. And this is generally the way that the drag coefficient is parameterized in models. You just do a drag coefficient as a function of U-turn, the wind speed at a 10-meter reference height. And these are our results, and these two gold parameterizations are the drag coefficients that's input into general circulation models. So you can see they don't have a dependence on U-turn, they just have a constant drag coefficient. These white points with the error bars are our results. And then these two parameterizations here are CD U-turn parameterizations for the open ocean. Okay, so that's not in sea ice, it's just pure open ocean over waves. So again, just focusing on the momentum fluxes. What we wanted, it was shown a few years ago that actually maybe U-turn isn't the best variable to parameterize momentum fluxes. Maybe you want to look at something else that tells you something about the ice concentration. Okay, so we have a really unique data set which covers conditions from the open ocean, which we had around this area, to the marginal ice zone, and right into pack ice, where we had maybe 90 to 100% sea ice concentration. So this is kind of the first preliminary result of my work on the turbulent fluxes. This is the drag coefficient as a function of SSMI sea ice concentration. So this is a satellite product that's released by the University of Bremen. It's just based on brightness temperature measurements. This is the platform satellite SSMI. And we have a really good agreement with Ed Andreas' 2010 parameterization. This kind of quadratic dependence on of the drag coefficient against sea ice concentration, which kind of makes sense. This plot is basically telling you that at intermediate levels of sea ice concentration, so where you've got partly open water and some big blocks of ice floating around, those are the conditions that you'd find the highest drag coefficient. So that's the conditions where most of the energy, the highest proportion of energy from the wind is being transferred into the sea ice and eventually the ocean. So yeah, this is the first result. Our future work is basically to include a flow distortion correction. So this was obtained by a colleague using computational fluid dynamics, and this is applied to the mean wind estimate. So this doesn't affect the turbulent fluxes, it just affects our mean wind speed estimates. That's yet to be done, but that'll be included very soon. These flux measurements will be compared against estimates from algorithms of different complexity, including the Shiba bulk flux algorithm, which is basically the only bulk flux algorithm for high latitude areas like the Arctic. We're going to parameterize these transfer coefficients in terms of other forcing variables as well as ice concentration. The transfer coefficients will be compared with those from a sea ice model, which has more detailed information on ice morphology, not just sea ice concentration. And we're going to investigate the role of turbulent exchange in the surface energy budget, so that's kind of the end goal of this project.